I'd like to review something called summation notation, or sometimes you see it called sigma notation. This is a sum, and we're going to look at all the different parts of this sum. So first, that big thing that's right in the middle, this weird looking symbol, that is a capital Greek letter sigma, and that tells you to add whenever you see that symbol. The k equals 1 down at the bottom tells you where you start. And k is just a dummy variable. It could have just as well have used any other letter of the alphabet. But in this case, we've chosen k. So you start at k equals 1, and you end at k equals 5. And then the 2k plus 1, those are the things that you're adding up. So if I want to look at this sum in detail, I know that I'm going to start at 1 and end at 5, and what you do is you take this expression, 2k plus 1, and you look at the k and you plug in 1, and then 2, 3, 4, all the way up to 5, and each time we're adding that expression, so 2k plus 1, so 2 times 1 plus 1 gets added to 2 times 2 plus 1, and so on all the way up to 2 times 5 plus 1. That's what this sigma tells you. It tells you to add. And so then you can calculate this, and you end up getting 35. Okay, let's look at some more examples. How about the sum from k equals 4 to 7 of k squared? So remember, the 4 is where you start, and the 7 is where you stop. So this would be 4 squared plus 5 squared plus 6 squared plus 7 squared. And you can calculate all this, and you would get 126. How about the sum from k equals 1 to 50 of 3? Well, in this case, there's no k in the actual expression. It's just a 3. So we just add up 3 a bunch of times. In fact, we add up 3 50 times. So this is the same thing as 50 times 3, or 150. Okay, so we just saw that the sum from k equals 1 to 50 of 3 was 150, just 50 times 3. So consider this. What if I have the sum from k equals 1 up to n of c, where c is any real number? Well, in this case, you might guess, and you would be right, that it would just be n times c. Okay, what about the sum from k equals 1 to n of k? So that would be 1 plus 2 plus 3 all the way up to n. So let's figure out how we would get a nice formula for a sum like this. So imagine looking at this sum, and I'll write it over here. So we have the sum, and this is from k equals 1 up to n, and it might take some practice learning how to write a sum like this, of k, and that equals 1 plus 2 plus 3 plus, and then these dots means you keep going all the way up to, and I'll write maybe n minus 1, and that's the term that would be right before n. Okay. And I'm going to do this again. You'll see why in a second here, why I'm going to do the same exact sum. This is the sum from k equals 1 to n of k. But I'm going to write it backwards. So I'm going to write the n first, and then the n minus 1, and then the n minus 2 term, and then the next would be n minus 3, n minus 4, all the way down until we got to 2, and then 1 would be the last term. And what I'm going to do is I'm going to add all of this up. So in this case, when I add the sum, I would get 2 times the sum from k equals 1 up to n of k. And that would equal, okay, so I'm going to get n plus 1. Okay, that's the first term. And then n minus 1 plus 2, that's also n plus 1. Okay, so this is n plus 1. And then I would get n minus 2 plus 3. That's also n plus 1. And if you think about it, all of the terms are going to be n plus 1. So even if we look at the last ones here, we have 2 plus n minus 1, that's n plus 1. And of course, n plus 1, yep, that's n plus 1. Okay. And if we add up all of these terms here, there are n of them. So this equals n times n plus 1. So if I want the sum itself, I just have to divide out that 2 that's in front, and I would get n times n plus 1 over 2. Okay, so we know these rules. The sum from k equals 1 to n of a constant is just n times the constant, and the sum from k equals 1 to n of k is n times n plus 1 all over 2. How would you deal with these sums? How about the sum from k equals 1 to n of 5k? Or maybe the sum from k equals 1 to n of k plus 2. So we saw before how to do this when we actually had a number for n on top, but what if we don't? What if it's just n in general? Okay, so let's look at the sum from k equals 1 to n of 5k. So that would look something like this. We would have 5 times 1 plus 5 times 2 plus 5 times 3 all the way up to 5 times n. And these are the terms we're adding together. Well, I can factor out the 5, and then I would just get 1 plus 2 plus 3 all the way up to n. And that's the sum of 5 times the sum of k equals 1 to n of k, and I know how to do that sum. I saw how to do that earlier. So the rule here is that if you have the sum of a constant, like in this case I have my 5 right here, times k, I can actually factor that 5 outside if it doesn't have anything at all to do with the k. Just bring the 5 right outside. Okay, what about the sum from k equals 1 to n of k plus 2? Well, in this case, that would be 1 plus 2 plus 2 plus 2 plus 3 plus 2 all the way up to n plus 2. And that's the same thing as, if I look at it the right way, I can kind of group all of the first part of each term together and the second part together. So I would get the 1 plus 2 plus 3 all the way up to n, all that grouped together, and then all the 2's that came after it grouped together. And that's the same thing as the sum from k equals 1 to n of k plus the sum from k equals 1 to n of 2. And I know how to do both of those sums. So the rule here is if you have a sum that consists of two things added together, then that's just the sum of the individual things. Okay, so some new notation here. Suppose I have the sum from k equals 1 to n of a sub k, and that's going to be a sub 1 plus a sub 2 plus a sub 3 all the way up to a sub n. And these are just ways of labeling the terms. So, for example, suppose I have the sum from k equals 1 to n of 6k minus 5. Well, that 6 times 1 minus 5 there, so we have our general term, 6k minus 5 is a sub k. The 6 times 1 minus 5 would be a sub 1. The 6 times 2 minus 5 would be a sub 2. And then we have a sub 3 all the way up to a sub n. All right, property 1 said that we can take the constant term and factor it outside of the sum. And now I'm writing it using the new notation, the a sub k notation. And remember that c has to be a constant that doesn't depend on k. And the proof of this, well, we saw that if we have this sum with the constant terms, we can just factor out the constant term. So if we have this sum, that's the definition of the summation, and then factoring out the c, that's the distributive property. And then we saw that this sum was the sum from k equals 1 to n of a sub k, and that's the definition of a summation. Property 2 said that if you have a sigma of a sub k plus b sub k, that would be two things added together, you can actually do the sum of the individual a sub k and b sub k's. And the proof of this, well, what we did was we wrote it out, and then we kind of grouped together all of the a sub 1's, a sub 2, a sub 3, in other words, the first half of each of the terms, and then we grouped together the second half of each of the terms. And being able to group all of these things together involves moving parentheses around and moving terms around. And if you really want to be specific here, that involves using associative property to move parentheses around and commutative property to move the order of the terms around. And then we see that once you do that, you get two separate sums, one for a sub k and one for b sub k. Now, you might guess that there is a similar thing when you are subtracting, and there is, and the proof is very, very similar. In fact, And let's see if you can supply the proof on your own. It's very similar to the proof that you saw for property 2. Okay, so the properties of sums. Property 1, you can factor out a constant. Property 2, the sum of two terms added together is just the sum of each of the individual terms when you add those together. And same thing with subtraction.